So when you called Bill, I began to reflect, among other things, on what I might say tonight. But I thought back to over the 40 years that I've been privileged to be involved in this expedition of exploration of the solar system, and reflected as to how transforming this adventure is made in our vision of where we are and who we are in this solar system and what the solar system is. This adventure that I've been so privileged to enjoy as a career, and today I'd like to share with you some memories, some history, some perspective, and lots of old friends, images and processes that we discovered along the way that so awed us. So how simplistic our views were 40 years ago, and then how incredibly they have expanded as we gradually became aware of the beauty and rich complexity of the planetary environments and processes in our solar system. And where have we come today is the subject of my talk. What do we look at now as the solar system has become sort of a commonplace in our backyard, and we've been through it a few times. And we're very comfortable in it. And as we now stand poised, I believe, in a far better position in perspective as we approach our next stage of exploration, the worlds of other solar systems that Ellen was talking about just a bit ago. So let's begin. So let's go back to the early 70s. How many of you here were here working in planetary science in the early 70s? A handful. Well, you can correct me. So we had just returned samples from the moon, and the lunar volcanism appeared to be ancient, lasting from something like 4 to 3 or 2.5 billion years ago at the youngest. We had Mariners 4, 6, and 7 fly by Mars, and Mars turned out not to have canals and vegetation everywhere, but to be kind of a red ball that was beaten up and heavily cratered. And ancient. The Grand Tour, which was our chance to sweep through the solar system from Jupiter to Pluto, had been canceled. Something we could do again in next century. And as we commenced planning and designing the Voyager missions, our insights as to what we might find in the outer solar system were very stilted. Matter of fact, I was put on the team not because I had some background in geology, but because I knew something about spacecraft and remote sensing systems developments. And of course, as you well know, the geology that blossomed from the moons of the outer planets are just stupendous. But we learned a lesson, didn't we? So, starting off on Voyager's journey, the first thing we did was we were approaching Io. Now, of course, Io we knew was kind of pastel orange, sort of reddish, and we knew it was going to be a dead old place. Right? And there it was. Behold, the first images of Io revealed lots of craters. Matter of fact, we were already counting the craters. And they looked just like crater curves. But the craters turned out to transform themselves as we got closer into calderas and obvious volcanic flows So at least it had had some sort of activity in the past. Remarkable. And then looming over Io's limb, we saw something, one of the young navigation engineers saw something that looked like it might be another satellite that we forgot about behind Io. And of course, it wasn't an illusion and it wasn't a distant moon. And as you know, Io exploded into our new vision as an active world of volcanism. But not everybody was totally unexpectant. Three authors, Peel, Casson, and Reynolds, published a prediction in March Science just at the time of Voyager's arrival that Io might well be volcanic, which I thought was a stupendous prediction. So Io's exhibits a whole wide variety of volcanic processes, and Galileo explored a plethora of them, and books have been published about them, and Rosalie will sign one for you if you like. And by the mid-'80s, we recognized that not only were there sulfur dioxide and sulfur molten products on the surface, but they were driven by molten silicates. We found sulfur dioxide, it appears to be in aquifers exploding out of cracks, and all through down to the polar regions as just a phenomenal set, and not a single crater. Have we found a crater yet that we believe to be an impact crater with Galileo? I don't know. I think not. I think there's more craters in Arizona than on than on Io. Yeah, Io was visited on Voyager 1's first encounter. Of course, we didn't think, that would be it, right? So at least we had one moon that was exciting in the outer solar system, and so we could proceed with crater counting for the rest. And Neptune's Triton, as Bill mentioned, was visited on Voyager 2's last encounter. And no one imagined that we would find activity at 37 Kelvin in a 14 µbar atmosphere at that distance from the sun. It gets even less sunlight than Titan. Amazing. But Triton surprised us, and two plumes, we call them geysers, and every time I call them geysers, they get my head slapped by several colleagues who actually work on geysers. So these two plumes, Malahani and Healy, down at the center part of the south polar, or the polar cap, I forget because it's the polar cap extends almost to the equator at this time. And as Bill mentioned, we had taken with a Vidicon on the Voyager spacecraft, the cameras at the time, a series of images, and here they are, of Malahani. And if you look carefully, these are about a total stereo angle of about 30 degrees. And there is a little tiny guy there, the same one, a little taller, and now oblique view. These have been projected to a common viewpoint. But I'll put them into a time lapse, the bottom two, and you can see this spire jetting out of the ground. Those columns, thought to be the order of a kilometer in diameter, rise out of the polar cap to a height of about 10 kilometers, where they intersect the base of the stratosphere. And the winds at that level must even be only a few microbars are cast downwind. And so models for this suggested that sunlight, and this isn't the only model, some people think there's still a chance that this is actually endogenically driven by some heat flow mechanism, but one that suffices for now because it explains the observation is that sunlight penetrates this transparent layer, kind of like a greenhouse window, traps the heat below that thin layer, maybe a few meters of nitrogen ice. The nitrogen sublimes, builds up pressure, migrates toward the vent, picks up dark particles, foo-foo dust, which is probably methane that's been irradiated and by plasmas and UV to turn it black. It's mixed with these dark particles and drives these jets aloft, the order of, as I said, 10 kilometers into the stratosphere of Triton. Now, so the solar system is starting to become our backyard, as I said. We're comfortable here. And so we now can grab a concept that we saw out at Triton and say, let's see if that doesn't work on something we discovered on Mars. And so we come back to what we call the black spiders that were, I think, originally identified by Malin and Edgett, and then explained by Hugh Kiefer back in 2000, or at least an explanation offered. But I've got something to show you how these change in time and how you might actually be able to see the plumbing analogous to the plumbing underneath the ice cap on Triton. So tying these two together. These are mock images. This is the Mars Observer, Mars Orbital Camera on Mars Global Surveyor. Originally Mars Observer, but as you know, that one didn't make it. These start out at equinox and go to southern summer solstice, which would be in Enceladus it's not Larry Soderblom, it's Enceladus, is basically the longitude of Mars in its orbit. And at a longitude of 270 is basically the middle of southern summer. So you're watching this as it defrosts. Down here, about all that's left is frost and there you see the subsurface plumbing that drives these plumes. So, as I said, gas that is collected migrates toward the central vent, and then up it comes, and the winds cast it across the surface of the ice. In this case, dark sand. And when you get to the final view, it's no longer visible because the same fine-grained sand that's coming out of the vents is the same as the surface itself after it's defrosted. And so, and there's the appropriate references. Now I don't have an image to actually show you these plumes airborne, but Ron Miller has created his impression. We've tried to capture these. I know that HiRISE has tried to capture them, but at least Ron, when he painted this, was clever enough to observe them at high phase angle and high emission angle, which really helps. Maybe we should try that as well. So Fred Whipple, how could we give a Whipple lecture without some comets, particularly as comets have started to become part of our lexicon of geological processes, and particularly in celebration of Isa Rosetta's and Philae's stupendous accomplishment over the last year, and just very recently. And some things that are starting to emerge, not just the obvious, which is the solar-driven jets that we've known for millions of years, at least some of our ancestors whose hands drug on the ground. But now we know that there are geologically active processes going on. And one of the things I had a lot of fun with was our first electric propulsion spacecraft that we used to chase down a comet. And now it's become a common way of getting around Dawn and others. And hopefully we'll use it for other things. But one thing, as Bill mentioned, the early Halley, of course, had been visited in 1981, and quite remarkable by the whole flotilla of missions. But Halley was at that time so close to the sun it had become quite active, and our ability to see the surface processes and the geological nature was quite difficult. But in this case, I want you to remember this feature over here, kind of a grayish area. One of the things you'll see in the plumes of and the gas jets of Borrelly are coming out of this sort of, if you imagine this to be kind of like a foot, and this is the bottom of the foot, the arch in the center. You can see plumes, and of course the Rosetta images of Churyumov Herosimenko, or P67 for the coward, are spectacular. So in comparing, remember I mentioned this feature here. Well, lo and behold, when we saw the Temple 1 images, we see a feature here that's very similar. And they're also close to the venting. In the case of Borrelly, the vents are coming out all through here. And so it looks as if some sort of a very universal cometary process is going on here. And so what comes out of, obviously, cometary jets, as they subside, they have to reduce in activity, and as they do, the stuff they're carrying, which is dust, largely dust captured in the gases, needs to go somewhere, and it's going to go back onto the surface in the low gravity environment. And we see the same kinds of features in the beautiful Rosetta Osiris images of the surface of P67. I thought I'd throw this in because there's been some discussion of whether or not Churyumov-Herosimenko is in fact two heads glued together. Well, remarkably, 4 out of the 6 comets, there's Hartley 2, the little one, P67, there's Borrelly, and here's Halley. 4 out of the 6 have this same sort of dumbbell shape. That's probably not a coincidence. And what we discovered with Borrelly is that, well, as you all know, when you took celestial mechanics in the 4th grade, as an object starts to rotate, any losses in the body, frictional losses, are going to cause it to migrate, so it's rotating around its c-axis, and the c-axis is going to be normal to the long axis, right? And of course, if that axis, if the erosion starts to occur on what would be the b-axis, then it can rotate around there. And so what I suspect is going on is kind of like a little boy eating an ear of corn, where he's only eating it in the middle. And so the c-axis is always going to stay in that position. We found that in the case of Borrelly, that it had oriented itself so that the rotational axis, the North Pole, if you want to call it that, ended up pointing directly at the sun at perihelion. And of course, when that is the situation, the sun is strutting on the North Pole 24 Borrelly hours a day, which aren't very long. And so it's basically burning a hole in through the middle, and in 10,000 or 100,000 years, it will be 2 pieces. but I doubt that it started out as 2. So far we've been out to Io, then out to Triton, then back to Mars, and back in between to some comets. And so next I'd like to turn to Enceladus. And Enceladus is a family of objects that has really astounded us. It's long been known to orbit in the diffuse E-ring, which is a wreath of dust around Saturn. And here is a Cassini image showing Enceladus in the beautiful image in the wide-angle view showing Enceladus in the E-ring. And Cassini, as you all know, discovered polar jets in the South Polar region. So far, we have not seen any elsewhere, concentrated only in the South Pole. Now, whether they're concentrated there now and they change with some secular or even periodic time scale to northern and southern, we don't know, but right now they're in the southern hemisphere. So let's talk a little bit about their character. So this image shows what originally was thought to be a single plume out of the South Polar region, originally seen in the ISS, which is the imaging subsystem on Cassini, but not sure at the time whether it was real or an artifact. Then MAG and the magnetometer and the ultraviolet spectrometer showed that there were clouds of both dust and water vapor coming out of this plume, or in the vicinity of Enceladus. Many flybys later, it was clear that they were concentrated in a plume centered at the South Pole. There's the North Pole. And then the ion neutral mass spectrometer detected not only water, but a whole plethora of hydrocarbons from methane and other more complex ones, as well as CO2, ammonia, and some radiogenic argon. Perhaps an interesting signal as to what might be helping with the heating. The geologic setting, here you see the ISS image of the South Polar region, colorized. This is Paul Schenk's creation, but these colors, the VIMS, which is the visible and infrared mapping spectrometers, show these to be coarse water ice, at least to be consistent with coarser water ice near the vents. And then ISS more recently has been able to break the plume apart and show that it's not a single plume, but it consists of hundreds of discrete plumes emerging out of what they call the tiger stripes across the South Polar region. But it's still a mystery as to what's driving it. Sears, which is the Cassini's composite infrared spectrometer, basically did an inventory of the total power coming out of these along these stripes and found it to be something in the neighborhood of 5 gigawatts. And VIMS, notice that the background temperature here, because Enceladus is among the brightest, if not the brightest, the highest albedo object in the solar system, then its surface temperature is going to be low. And so the background temperature out here is in the 60, 75 Kelvin range, but Sears sees temperatures in the tiger stripes of 130 to 175 Kelvin. VIMS, with a high resolution pass across this particular tiger stripe, detected a temperature close to 200 Kelvin. And all of that adds up to something of the order of 5 gigawatts. So what's driving the plume? The source was debated, and still is debated. one of the problems is that the tidal models that I'll get to shortly can account, most of them could only account for a gigawatt out of the 5 gigawatts of power, but still that's within an order of magnitude. So were the plumes coming out of some shallow subliming sort of comet-like or Mars-like or Triton-like process, or were they coming out of a deep-seated source like an ocean? And then in 2011, the CDA, which is the Cosmic Dust Analyzer, found that 99% of the grains that are coming out of Enceladus' plumes are salty. And their contention is that it is impossible or very improbable to get salty crystals out of simple sublimation. And so their conclusion was it points directly to a subsurface salty ocean. So as I mentioned, tidal heating is the primary energy source believed to drive these plumes, but only roughly a gigawatt out of the 5 gigawatts could be accounted for. Then in 2013, VIMS found that these plumes were most active well, here I've got an arrow showing that the plumes brightened up by basically a factor of 4 at apoapsis, which is at apoapsis, then at periapsis. So when it's farthest from Saturn, basically, these cracks open up and out comes the gases. And at the same time, a model by Herford et al. Suggested that that the closing and opening of these fractures modulated by the orbital position was to be expected, and likely that this process could be concentrated in the south polar region. So the evidence seemed to be pointing to a liquid subsurface ocean. And then just a short time ago, the RSS gravity analysis from 3 flybys showed a south polar gravity anomaly that is consistent with a subsurface ocean and 30 to 40 kilometers in depth and extending up to 50 degrees south latitude. And so our model now, here you see the lens of this south polar ocean, some 30 kilometers down. And the issue of the energy sources still remains unresolved. One of the problems is keeping this ocean from freezing. And one model that suggests that, as I just mentioned, the heating is concentrated in the crust of the south polar region, so keeping this local ocean, in other words, the dissipation and heating is concentrated in a smaller geographic area. So, one of the questions, and Ellen mentioned this, is Europa. Is Europa active? So Voyager and Galileo both showed that it surfaced to be extremely young, very few impact craters on this jumbled tectonic surface on Europa, and again, subsurface oceans. And all 3 of the Galilean satellites were found by Galileo to have subsurface oceans, as Margie can tell us all about. The difference is that in the case of Ganymede and Callisto, those oceans are a couple of 100 kilometers below the surface. In the case of Europa, the ocean may be only 15 kilometers. At least that is one model. And as many of you know, the Hubble spectrograph, space telescope imaging spectrograph found water vapor near Europa and suggesting actually two 200-kilometer high plumes coming out of the South Pole. And Lorentz Roth's explanation is that the simplest explanation is that these, like Enceladus, are plumes of water vapor coming out of Europa's south polar region, and Europa is now the target of NASA's next major outer planet mission. Keep your fingers crossed. So the last subject, and fortunately, I'm going to talk a bit about Titan. And fortunately, my slides are not the same as Ellen's. A little bit different. So back to the pre-Voyager time. So Kuiper discovered that Neptune had an atmosphere of with methane in it back in 1944, but not much new was learned until the 1970s, and telescopic observations showed that ethane and methane existed in the atmosphere, and a variety of other complex molecules, suggesting that a chemical factory was operating in the atmosphere. 1980, Voyager confirmed Titan's smoggy atmosphere was thick. It's 1.5 bars, so it's thicker, it's higher pressure than the Earth's atmosphere at the surface, and 95 Kelvin. And Voyager again identified even a greater range of hydrocarbons, and which led to predictions of a thick layer of organics over 4.5 billion years. As a matter of fact, methane should generate hundreds of meters of ethane, acetylene, propane, hydrogen cyanide, and a whole range of other hydrocarbons and other ingredients. So because the methane would disappear, the current methane in Titan's atmosphere would disappear in only a few million years, we started to look for a long-lived source of the methane, and maybe a global ocean was implied, or subsurface, vast subsurface reservoirs. And so, but in the 1990s, Earth-based spectra showed that Titan's surface was not consistent with either water ice on a global scale or a global liquid hydrocarbon ocean on a global scale. And then Peter Smith's Hubble images in 1996 picked out Xanadu, a bright continental scale feature at the equator, and the global oceans were ruled out. So June 2004, Cassini-Huygens enters Saturn orbit. In October of 2004, VIMS, the Visual Infrared Mapping Spectrometer, began to map Titan's surface through the thick haze. And as the atmosphere cleared through as VIMS saw through to the surface, no global oceans or seas, no obvious bodies of liquid appeared anywhere on Titan's surface. Rather, these dark equatorial bands that Ellen talked about, which the radar showed us to be vast sand seas with longitudinal sand dunes. So an active process going on again. So, and then in Christmas 2004, the Huygens probe is released And at an altitude of something like 90 kilometers, we break through the haze, and we're headed down to a landing point down in here. This looked like it was an arrow pointing to the landing site. As we approached the surface, we saw a surface scoured with fluvial dissection at the scale of a few hundred meters. And at the surface, we found rounded boulders suggesting, in these scoured surfaces, suggesting floods of liquid methane must have occurred across these plains. And during the descent, as you saw, up in this region, we saw what looked like dendritic patterns. As a matter of fact, this image started to look very Earth-like. This looks like longshore bars and features the scour, and the plains is out here. And so this dissected highlands is a different item. And we had stereo images that show what this looks like. Now, this is a vertical exaggeration of 1:1, which is rarely done. And when we show, usually in any kind of a stereo model, we jack it up to 3:1 or 10:1 so you can see the topography. But this is 1:1 topography. And so the dendritic drainages and so rainfall had to be going on in Titan's recent past. But where, if we couldn't find the lakes, where was the liquid methane? Was it in the subsurface, or was it in some lakes we hadn't found yet? In 2005, the imaging system picked out a feature in the South Polar region, which has become Ontario-Locus, which looked like a lake, suggestive. And then in 2006, the radar system discovered a whole range of lakes near the North Polar region. And those are some of the smaller lakes, and adjacent to those were vast seas that Ellen talked about. VIMS detected ethane, liquid ethane in the lakes, and also VIMS captured this reflection you've seen. And so the clinchers came that these had to be liquids. The specular reflection was off of close to Krakenmaria, one of the big, large seas of the northern hemisphere. Also, as Ellen mentioned, ISS images showed evidence of rainfall. She talked about the equatorial case, which I'll get to in a minute, but this is in the South Polar region. This is 2005. There's Ontario-Locus. These are clouds. This is the work of Zibby Turtle. 2004 was the prior image. 11 months later, you notice this dark area emerged and believed to be wetted surface, and then this region here was found by VIMS to freeze just less than a year later. This is several years later. In the equatorial case, this is the arrow, which is a cloud, not an arrow. If you'll look down in this zone right here, this is before the rain occurred. And then in here, I'm sorry about the lights in the room. And then and finally that wet ground disappeared. So as Ellen mentioned, we know that the polar lakes are concentrated in the North Polar region, and in fact, there may be an explanation for that, which is our Milankovitch cycles, or like Milankovitch cycles for the Earth. You can see that the insolation peak in the north and south switches on something like a 45,000-year cycle. And this image, this animation running back in time, you can see that the perihelion, aphelion positions of summer solstice in the northern and southern hemispheres is switching basically every 45,000 years. So in this ultra-cold environment, where we would have expected little in terms of activity, nature simply switched out the chemistry. And what we've learned in exploring this solar system, our solar system, is that all you really needed to do was go to the Handbook of Chemistry and Physics and look up the common cosmically abundant material, which would be mobile and liquid at those temperatures, and it would be there and it would drive the geology. And like Earth's hydrological cycle, methane's methanological cycle, there's a word, harbors all sorts of weather and climate processes rich on that world. And so in summary, Titan proves spectacular beyond any imagination, and it's a far cry from what we might have anticipated beneath this smoggy cloak. And what I've been amazed by is that as we talk about geomorphology and processes on Titan, the way it looks like it came straight out of a textbook of Earth's geomorphology. And so not quite the barren, lifeless world. And so my closing slide, Bill. So what lessons can we take from these active places into the next phase of exploration? When the Voyagers were launched, our naivete allowed only that planet Earth was dynamically active. But exploring our solar system, our own cosmic backyard, has awed us with the unforeseen complexity and scientific beauty and its rich activity. And I believe we are now far better poised for our beginning exploration of the next set of solar systems. Thank you.
What a rich synthesis. We do have some time for a few questions. If you'll come to the microphone in the center there, that would help. But I'll just start while some people line up and just ask you, would you care to offer any predictions for what we'll see at Pluto next summer?
I think it'll be bizarre. I know it'll be bizarre. So that's the lesson from the past.
Sir.
What do you see as the logical next step? Personally, I'm fascinated by Titan, and I wish we had a radioactive source on the. You got a mass spec down on Titan, as I remember. And so, what do you see for a next step?
Well, the next step is a whole plethora of possible missions, which have been developed. Everything from airplanes to yellow submarines floating through the atmosphere, as Carl Sagan would have imagined. I think Ellen would like to be in a dinghy on one of the polar seas. There are missions imagined to land there and scoop goop up from the bottom and analyze it. And so the biggest problem is that the seasons change on Titan at almost a glacial pace. And so the North Polar region, which is the most exciting and in some ways technically available engineering-wise because of a large body of liquid to hit, will soon be in darkness. But if we don't get our economy and our space program back out of darkness, we may be ready for the next season anyway. But Titan remains at a very high priority in all of our minds for future exploration.